oscillator, same 5. This experiment we are going to explain today. See this is the experiment circuit diagram for Wein bridge oscillator. In this circuit, this is the Wein bridge, and in these 4 arms, resistance R1, R2, R3, R4 are connected in this fashion. This is capacitor C1 of 0.1 microfarad is fixed capacitor. This another capacitor C2, which is variable capacitor, we are going to change. This is variable resistor. It is nothing but the pot we are connected in the circuit, and this is the R4. From this circuit, it is connected to IC741 op-amp. This is non-inverting terminal, this is inverting terminal, and this inverting terminal is connected at this junction and non-inverting terminal is connected at this junction. For this 741 op-amp, dual power supply is required. Hence, we have to connect positive 12 volt, negative 12 volt with respect to ground. 6 number, that is output of op-amp 741, is connected in this circuit at this junction, and this junction is grounded. Now see actually the circuit diagram. Here in this circuit diagram, this is the Wein bridge. These 4 resistors are connected. This one capacitor which is fixed, and these 3 capacitors C1, C2, C3 are connected, which are variable capacitor. The variable resistor, that is pot, this is the pot we have to adjust, and by adjusting the pot we can change the frequency. Here this P1 and P2, these 2 ports are there. P2 is inverting input and P3 is non-inverting input, which is internally connected to measure the input voltages. Now how to make the connections? From this dual power supply, positive 12 volt, we have to connect over here. It is written here, see, plus 12 volt. From negative 12 volt of this dual power supply, connect this to in this terminal negative 12 volt, and ground terminal is connected to the ground. After making these connections, from CRO, 2 probes we have to use, one probe for input, another for output. Output 6 number is connected. This one which is inverting and non-inverting we have to measure in the circuit each time, and this ground is connected to the negative terminal of these probes. Now see here, these are the apparatus which are required here: oscillator, CRO, dual power supply, built up circuit of Wein bridge oscillator, and connecting wires. The formula for that, F equal to 1 upon 2 pi R1 C1 under root R1 C1 R2 C2. The values of this resistor, R1 is 10K fixed, R2 is fixed, C1 is fixed, and C2 we are changing. C2 we are changing the values 0.1, 0.2, 0.3. The formula for the calculation of frequency, 1 upon 2 pi under root R1 C1 R2 C2, and by using these values we have to make the calculation, and after doing calculation we will get the frequency. Here for these values we are getting this frequency. Now see this observation table. In this observation table, voltage at output terminal. So this voltage at output terminal on CRO we have to see. Now look here, on this CRO, upper one is input wave and lower one is output wave. That small one is input wave and bigger one is output wave. Actually it is continuously visible, but in this shooting you can see uncontinuously breaking waves. So here we have to measure the voltage of this wave, input wave as well as the output wave. So how to measure the voltage? Upper peak to lower peak. Upper peak to lower peak. This gives the number of divisions multiply by voltage per division knob for this output probe. And for input, we have connected to the non-inverting. So for this upper peak to lower peak, multiply by voltage per knob division, that gives the voltage of this input. So voltage you can measure on CRO. Now see in this observation table, initially when it is not connected anywhere, this pin, that time one capacitor is internally connected and that capacitor is 0.1 microfarad. This 0.1 microfarad is connected in the circuit, and for this we are getting the wave on CRO like this. So to get the clear sine wave, we have to adjust the pot, and by adjusting the pot, see on CRO, clear sine wave will be observed. This is the sine wave which we are getting by adjusting the pot. Now for this sine waves, we have to measure the time period, and from that we can calculate the frequency. So in this observation table, we have to measure the output terminal, that is output voltage VO peak to peak. For this sine wave, this is the output sine wave, and for this output sine wave, we have to measure upper peak to lower peak, this number of divisions 1, 2, 3, 4, multiply by voltage per division knob. It is at 5. So 4 into 5, that is equal to 20. So see here, it is 20. This is the peak to peak voltage 20. Now non-inverting input terminal. Here we have connected the another probe at non-inverting input terminal. It is written here, see, non-inverting input terminal. We are connected here, and we have to measure the voltage for this input wave. So here for this input wave, number of divisions covers from upper peak to lower peak, multiply by voltage per knob division, that we will get the non-inverting input. Similarly, we have to connect, now remove this pin from here and connect it to inverting. For this inverting, we have to measure on CRO number of divisions cover for this input wave, upper peak to lower peak, number of divisions multiply by this knob. That gives the inverting input voltage. So in your observation table, we measure the output voltage, input non-inverting voltage, input inverting voltage. After recording this, we have to find out the time period for output wave. For this output wave, we have to measure the time period. So how to measure the time period? Number of divisions covered by one cycle from this peak to this peak. Number of divisions. So by adjusting here number of divisions, we can measure, make it perfect sine wave. So we can match it. See, 1, 2, 3, 3.4 multiply by time base. Number of division covered by one cycle multiply by time base. So time base is at 0.5. So this 3.4 multiply by 0.5, that is equal to 1.7 millisecond is the time period of this wave. For capacitor C1, C2 is equal to 0.1 microfarad. And reciprocal of that will use the frequency of that wave. This is the frequency. From that you can calculate the beta factor V2 upon VO, that values we have. Gain we can calculate VO upon V1. Now for second value of capacitor, insert this pin in this terminal, and see here, now the waves are disappear. By adjusting the pot, again we have to adjust the value of this variable resistor such that we will get the sine wave on CRO. See, for this value we are getting the wave. This is the input wave and this is output wave. For this input and output wave, again we have to measure the input voltage, output voltage. Now this is connected to the inverting input, we can measure the input voltage, upper peak to lower peak, multiply by number of divisions, multiply by voltage per division knob. For output wave, upper peak to lower peak, number of divisions, multiply by voltage knob, that gives the output voltage. And for time period, number of divisions covers by one cycle from this peak to this peak, 1, 2, 3, 4, 4.8, multiply by this 0.5. It becomes 2.4. Now time period is increased, means frequency is decreased. So another frequency we can calculate by using that. Now just remove this pin from here and insert over here. Again these waves are disappear by adjusting the pot. This variable resistance, we have to obtain the waves on CRO. See this? This upper one is input and this is output. Inverting, non-inverting, both input we have to measure. And for output wave, we have to measure the voltage, upper peak to lower peak, multiply by this number of divisions, multiply by voltage per division knob. And for calculating the time period, the number of divisions covered by one cycle, this peak to this peak, multiply by time base. This is now, see how many divisions? 1, 2, 3, multiply by 1. Again it is increased. So 3 milliseconds and reciprocal of that gives the frequency. As time period increases, the frequency is reducing, and from that we can calculate the frequency for each cycle. This is the first part of Wein bridge oscillator.